responses of building contents are sliding, rocking, jumping, and combination. But in seismic studies, rocking play a major role due to the probability of overturning, which may cause fatal accidents. So this is one of the examples for the large scale shake table test from Japanese team. From here, we can clearly see structural than the structural parts. And as I told earlier, there are two modes there. One is sliding, other one is rocking. The sliding won't cause any that much issues, but for the rocking, it will overturn and cause fatal accidents. So our thesis focus on rocking category. So these are some examples of overturning building blocks during earthquake. Especially for the hospital buildings and healthcare facilities, those performance is essential in the after effects of moderate to high magnitude earthquake ground motions. So these are the examples for the non-structural components. In our study, we majorly focus on rectangular components. The rectangular components can be divided by asymmetric and symmetric. So in our case, we choose asymmetric one, so which will include the symmetric as well. And we can idealize the model like this rectangular element. As we can see, I idealize as an asymmetric one. Here, R is the sizing parameter. Sizing parameter is the distance between center of mass and the corner, and the critical angle. There are two main parameters: sizing parameter and the critical angle alpha. Here, for this asymmetric block, there are two critical angle and two sizing parameters are there. So, critical angle means for this rotation, that is the maximum angle it can rotate up to the overturning. For this side rotation, this is the maximum angle it can rotate up to the overturning. So these are the typical value for the R value, 0.5 to 2 meter. So there are several studies they conducted for the symmetric specimen, but for the asymmetric specimen, which conducted the shake table test, and he considered the same size, and he applied the same ground motions. And as we can clearly see that the symmetric block experienced a minimal rocking. However, the asymmetric block overturned, and high rocking also there, and overturned in the more slender direction. Then other one, the content inside the bookshelves. So here Daishano conducted the content inside the bookshelves by doing shake table test. Here those are the positive effects conducted by content inside the blocks. So content inside the blocks can increase the peak ground acceleration that trigger the rocking motion. As clearly we can see that this one is 0.27, this one is 0.441, and the reducing time of rocking acceleration. So content inside the blocks have positive effects considering this point of there. Then overview for the flow acceleration. When the flow acceleration is there, so we need to add both flow excitation and the ground motion. In many past studies, researchers use ground acceleration instead of flow acceleration, but this assumption is not valid for the high-rise building. Majorly because in high-rise building, this one is the response spectra for the 40-story building. As we can see, this one is the ground motion response spectra. So this one is smooth and flat one is there. But however, for the flow acceleration, so this one is, we can clearly see that flow acceleration is much different than the ground acceleration. It's also the flow acceleration as well. Then we'll go for the analytical model. So when he derived he put the parameter, second one, coefficient of restitution. The coefficient of restitution is energy loss. When it's rocking, each time rocking, there is some energy loss is there. So that is coefficient of restitution is defined by angular velocity. So this is the proof for the coefficient of restitution for symmetrical block. So Hausmann's assumptions are impacted force are concentrated at the impact points. So he proved that the coefficient of restitution is dependent only in the critical angle alpha. There are two sizing parameter. When the theta less than equal to 0, we have to consider the greater than equal to alpha 2. When the dissipation is high for this side, dissipation is low. Then we'll go for the governing equation for the rocking. So these are the equation from the house. As you can see, when we put in equilibrium of movement about the center of rotations, so this one is theta less than 0. Theta greater than the damping parameter. Then for the asymmetric block, the same concept we can apply, but each case of theta less than 0, the different energy loss we have. So using this one, so we can develop, we can solve this equation using MATLAB Simulink with fourth order Kunchi-Kutta integration scheme. We use time step as 1 millisecond. Now we will go for the overview for the fragility graph. So as I said, this one is a governing equation. In practically a high-rise building, various sizes of blocks are in different floors. So this is not effective to simulate analytical model for each axis. It's the intensity measure. Here for the example, I consider peak intensity measure is a motion parameter to define the input intensity of flow shaking. So that is depend on the applied ground motions. Then this one is the probability. Probability demand parameter greater than equal to capacity. We can derive by theta alpha because max alpha for symmetrical block. So if we develop the fragility graph like this, so if we know the peak ground acceleration for a particular block, we can get in past studies. These are the two common intensity measures they use. IM1 is equal to peak flow acceleration and peak flow velocity. Then when we my continuation of the last scene here, named Nima. So this one is responsible for the ground motion. He adapted the Hausner's analytical model for the symmetrical block, and he compared the analytical solution and experimental results, and he proved that analytical solutions are much predicted for the symmetrical block. And he finally did the regression analysis to find the best intensity measure to develop the fragility graph for both ground and flow acceleration for one building only. And he considered only the symmetrical block. Best intensity measure was IM2, that's dependent on peak flow velocity. Here he concluded that, as we can see clearly, so the red one is the ground one, the blue one is the flow one. He concluded that ground acceleration is more vulnerable than the flow acceleration. He concluded that this one is the best intensity measure, and he concluded ground acceleration is more vulnerable than the flow acceleration. This limitation, he only considered the symmetrical blocks, and he only considered when we include the asymmetric block, this intensity measure is the best measure. The answer is no. I'll tell the reason why later. This, if you consider the asymmetric block, still the building blocks are more vulnerable for the ground acceleration. Answer is no. I'll explain the reason later. So this one is a problem statement. I already explained those things. In our studies, we consider symmetrical block and asymmetrical block, and with the content inside, and we develop universal fragility graph for both ground and flow acceleration for several type of building. For performance-based design, the identification of effective intensity measure is one of the major important to develop the fragility graph for the loss assignment. Our objective, our first objective is create a numerical model for the asymmetric building blocks. In our case, we choose two blocks. One is for the symmetrical block, other one is for the asymmetric block. Our derived asymmetric block it will work well for the symmetrical case as well. Firstly, we have to create a numerical model for the asymmetric block. Then we have to verify the numerical model by doing experimental results by shake table. The third one, so examine the behavior of building blocks at various flow layers. We are considering. In fourth one, we consider the content inside the block. So here in third case, this asymmetric block with packed books inside. This one is the pack side of the bookshelf. So if you pack the books properly like this, these books also act like a rigid behavior, and it become more asymmetric behavior compared to the specimen without books. So other one is asymmetric block with loosened books inside. Here I consider this loosened books inside because to allow to move relativity of the block. It can allow to move relative to the this block, but same inside. Then the fifth case, the loosen is there, but we loosen outside the block, as you can see. So when we are putting outside the block, this case will become symmetrical identical case. I'll show the reason why later. This one is the overall methodology for the active objectives. First one is we have to select the ground motions. So our seismic zone is moderate to high seismic hazard zone. So depending on that one, we can create the dB level. So selection of ground motion. We choose 8 suitable ground motions based on our target response spectrum. And for the shallow crystal earthquake, fault type is strike slip, and magnitude 6.2 to 7.3. These are the ground motion selected. But our shake table limitation is 70 mm displacement. So that's what we choose H1 characteristics of each ground motions. And we choose three of these ground motions to compare our analytical results and the experimental results. And this one is H1 response spectra for the 8 selected ground motion. We can clearly see that the red one is the target response spectra. Then arithmetic mean response spectra is will match. And this one for the H2 ground motions. Next, we'll go for the selection of high-rise building. Here we choose 4 different type of high-rise building: 40-story, 33-story, 23-story, and 12-story. So these are the parameters. So all different type of buildings are modeled in ETABS. We choose 8 ground motions. The ground motions are applied in the weak direction, and we did linear time history analysis because we focus on non-structural components. We are not considering the structural part. That's what we choose linear time history analysis. Then we can get the flow acceleration time histories. So this one is a mode shape for the 40-story building, 33-story building, and 23-story building, and 12-story building. So here as you can see, this one is the response spectrum for the mean response spectrum considering all the ground motions. This one is ground motion and flow motion. Here as you can see, for the flow acceleration, high spectral accelerations are found in first, second, and third mode of x direction. So we can clearly see that the ground motion is not equal as flow acceleration. So this one is wide band. This the flow acceleration is become as a narrow band. The same thing for the 33-story building. We can get higher spectral acceleration in particular modes. Same thing for the 23-story building and 12-story building. So next, we have to check for the accuracy of our numerical model. So this one we compare our analytical model with past analytical model. So this one we choose for the Marquis paper. We applied Pacific Dam earthquake. It's well matched with the past analytical model. Here we choose Hausman's coefficient. Okay, next we compare our analytical model with past experimental results. The first red one shows the which experimental results. Here some interesting things have found. So the red one shows the experimental results of his paper. Then the blue one shows his analytical results. And analytical results predicted much well with his experimental results. cells. Here we choose E. Hausner for the symmetrical block. Okay, now we compare for the asymmetric block for the free vibration. Here the same thing. For the asymmetric block, we have to reduce the Hausner's coefficient to well match with the experimental results. So the yellow one is for the Hausner's coefficient of restitution. Hausner's coefficient of restitution is angular velocity after the impact over angular velocity before the impact. So we have to reduce by this factor, then only it will match properly. So Hausner's coefficient of energy loss is less than the actual one. So in actually the energy loss is high. So our experimental set, we can test ground and flow acceleration, all type of ground and flow acceleration from using AIT shake table. Here our shake table is uniaxial shake table. These are dimension and our capacity is plus or minus 75 mm. And this one is side view and spectrometer. One is at the shake table itself, other one is at the top of the bookshelf. So these are the experimental setup. We use safety rope methods to prevent the safety of the block and the books. And we use carpet to ensure that the block is not sliding. We mainly focus on the rocking, that's what. So effect of eccentricity in our asymmetric specimen. So this is side view of the bookshelf. Here we can see the width of the bookshelf is 280 mm, but effective width is only 220 mm. This one first one. The second one, there 2.5 mm back seat is there. Third one, we consider the content inside the bookshelf as well. Okay, these are the 6 cases I explained earlier. One is symmetrical case, other one is asymmetrical case. Then pack book inside. This will become as a rigid one. Then loosen books inside. Then loosen book outside. So this one is a comparison of the specimen number 1 and number 2. For the symmetrical specimen, we can see that critical angle ratio alpha 1 or alpha 2 nearly 1. So this one is the symmetrical specimen. For our asymmetrical block, the critical angle ratio become 1.74. This is a summary of all our cases. So from symmetrical to asymmetric, the critical angle ratio is increased by 28%, likewise. But for the pack book inside, angle ratio is almost same. But if you put loosen books outside, the critical angle ratio become almost 1. So it will become as a symmetrical specimen.
1 second. The determined center of mass here is from the numerical calculation, right?
Yes,
you calculate.
I calculate by hand.
Okay, hand calculation.
We had to find B1, B2, alpha 1, alpha 2 cells. Those are the input parameters.
Yeah, please continue. I just, well, calculation sometimes is not as accurate as it is from the measurement. Okay.
This is a summary for all our 5 different cases. And
because there's a LVDT inside the hydraulic actuator, so you can pull out the displacement time history. Oh, okay. So you differentiate. Okay. So the thick red line. All right. That's from the hydraulic actuator. Okay.
Yes, sir.
Okay. Okay.
As you said,
Right.
so we applied the displacement time history. We can't apply directly to the acceleration time history. We apply the displacement time history, sir.
Yeah. Then let me try. I try to write. Okay. Somewhere around here. What is going on? Why is it like off by so much like this? And how do you cope with this situation?
Because, sir, this is our input acceleration, but we applied only the displacement time history. So,
Yeah.
so that may be also the reason. And sir, our accelerometers.
Actually, you might also plot out the frequency domain response of this acceleration. And it might be at some certain frequency that the accelerometer might not be sensitive, so it cannot catch, or it gives you the wrong. So this is accelerator. Okay, and then all right, you have it. Okay. What? This is a response spectrum, 5% damping.
Yes, sir.
I think Sivaram, you need to explain. This is what. So this is a measurement of real acceleration of check table, right?
Yes, sir. Yes, sir.
And what is this?
Input acceleration before converting to the displacement time history. So
this is your target acceleration you want to produce by check table.
Yes, sir. Yes, sir. It's a target.
So actually, this is his target record.
Okay.
And he actually integrate into velocity. He integrate into displacement.
Okay.
And he used this one to drive the actuator.
Okay.
And then from that, he got acceleration.
Okay. Accelerometer.
This one. Yeah, this one is this, and this one is that. It's quite resemble, quite close, except for short period.
High frequency, yes.
So basically, it is sort of usable to somewhere around here, like this is one. So about less than 2 Hertz, that the signal is okay. The input and the output are identical, right?
Yes, sir. Yes.
But when the frequency is greater than 2 Hertz, just approximately 2 Hertz, yeah, then you have a problem in there, right? So that's the observation.
And noise of the accelerometer also may be the issue, sir.
What?
Noise.
What?
Noise of the
Accelerometers. But then that in that case you have to, I mean, put the accelerometer at the quiet place and try to see the noise level or so, right?
Yeah, but I think that the key point is it doesn't have to make a perfect match with the input. Because whatever he record, that will be the input into his
analytical model.
Numerical model.
Okay, all right. So it is just giving the excitation to the system, to the block, right?
Yes, sir.
But the input, the real input to the analytical model is from the accelerometer that's installed at the base.
Yes.
So, okay, all right. Okay, but you do not have the frequency domain response of 4 accelerometer compare to each other. You have only just the time domain.
Yes, sir. Yes, sir.
Okay. Well, they looks pretty much the same. Okay, but that will be great to have. Okay. Okay, continue, please.
Okay, sir. And next, we'll focus on validation of numerical model. So for the validation, we have to compare our analytical model with our experimental results. Now, as Professor explained, we use two accelerometer for our comparison purposes. So one is attached at the shake table, one is at the top of the bookshelf. So we input the measured acceleration of accelerometer 1 to our analytical model, and we try to simulate the equation for accelerometer 2. Then we measure the accelerometer 2 and we just compare the equation from the analytical model. So from that, we can compare the analytical results and the experimental results. In last year, Nima, he didn't consider the effect by the G sin theta. But here in our comparison, we included the G sin theta as well. And accelerometer also we can use as the angular measurement device. So when there is a zero angular velocity or zero angular acceleration, we can use the accelerometer as the angular measurement device. I explain this because we did free vibration test for the symmetrical block. So this one, this one the results for the free vibration test for the symmetrical block. So we put initial angle minus 5.8, then this green one for the Hausner's coefficient of restitution, and the red one for our experimental results. Then the blue one, we convert the Hausner's coefficient of restitution by some small factor. Even for small factor, it reduced drastically, and it properly matched with our experimental results. So for comparison purposes, comparison between experimental and the analytical time history purposes, we have to scale the energy loss. Energy loss of the experimental one always higher than the Hausner's coefficient of restitutions. So we did the free vibration test for the asymmetrical specimen as well. So here we have to scale down by this 0.92. For the asymmetrical specimen, we can see the difference of both sides. The cylinder side have higher angle acceleration. Cylinder size means the positive side. Positive side have always higher angle acceleration, and it overturn also in this side, in the cylinder direction.
Oh wait. Come back. So you are about to say that you are happy with of this. I mean, do you just expect the magnitude here and there for the top side and bottom side, or should you also expect the phase matching of the signal that you get from the measurement and from the numerical analysis?
No. So in this case, sir, I just want to show that I don't do like that, sir. I just want to show that the angle acceleration at the cylinder direction always higher than the other side. I mean, the rocking is higher in this direction. So even though the critical angle is small, the rocking always higher in this direction. But
then you expect to see just the match in the magnitude of two different sides, but the phase of the signal and that is not matched. I wonder if it is not important or what.
Yes, we tried to match, sir, but we couldn't because, as I said earlier, because of the Hausner's coefficient, its effect much when comparing our time history results. So here we can see the time for the Hausner's energy loss, E1 and E2, the green signal is coming like that. Nearly it rocking up to the 30 seconds. But when we reduce the Hausman's coefficient, if we increase the energy loss, so it will match. This is the maximum match we can obtain.
Okay, so as of now, there is no other mechanism that you can think of, sort of, right? So the best match come from the manipulations of the Hausner coefficients.
Yes, sir.
Okay, all right. So there must be some other thing, right? Like the energy loss, which is within the material. Like if you use the bookshelf that is made of steel, in comparison with the MDF board, like what you're using, maybe the impact point could absorb energy or something like that could happen. So, okay, all right, yeah, something that it is not in your scope of study.
Yes, sir. So when we are comparing the time history only, we need to reduce the Hausner's coefficient. But for our overturning results, the peak ground acceleration at overturning, so we got the nearly same result. I'll show you that later, sir. So we can still use the Hausner's model. So that's what.
Okay, yeah, I get the point. Limitations we have. Okay, fine. Okay.
And these are the two selected ground motion just to show the comparison purposes. This one for the symmetrical bookshelf when excited by imperial valley. Here the red one is our experimental results, and the blue one is our analytical model, and the green one is the senior's numerical model without considering the effect by G sin theta. So we can predict a little bit much better than him because including the G sin theta. Here we can see the red one and the blue one much little bit better than him. And this one for the symmetrical bookshelf for Chan Valley earthquake, this still not properly matching, but the boundaries lines are same. It predicted much better for the boundary line.
Okay.
For the symmetrical bookshelf, the boundary line same for both sides, but for the asymmetrical block, the boundary line won't be the same. As I said earlier, it will always high angle acceleration at the cylinder direction and overturn also in the cylinder direction as well. So, as I said earlier, in experimentally, the energy dissipation by the Hausman is underestimated to the compared to the actual one. But we don't know that when we are developing the Fragility Graph, we don't know that for which case what is the Hausman's coefficient of factor we have to use. So that's what we use, only the Hausman's coefficient of distribution E1 and E2, and we compare our analytical and the experimental results. As we can clearly see that it predicted well for the peak ground acceleration and peak flow acceleration at overturning. In all the cases, analytical results are a little bit higher than the experimental results. So without correction or with correction of the Hausman's coefficient of distribution, overturning can be well predicted by our model. But to have a better time history match, we have to reduce the Hausman's coefficient. We have to put high energy loss for the analytical model. So then only the time history will match. So this one is asymmetric bookshelf with compacted books. So as we can see, there is no any related movement between books and the bookshelf. So the books became as a rigid one here. So still
just a very quick question, because normally when we see the earthquake videos from various things, we find that the contents are falling out. So is there a special reason why these books are not falling out? or have they been glued, or what happened? Because I often see that content fly out first. So is it specially related to books or something else?
Yes, sir. So that's a good
Or
question.
the folder is too wide and the depth is covering the whole width, so it cannot slide or something.
Yes, sir. The one of the major reason is, so this one is an asymmetrical bookshelf, sir. So as we can clearly see that it always rocking in cylinder direction, not in other way around. So in backside there is the back sheet is there, sir. So it will touch the back sheet. So
I see. I understand your point. Right. So if it was cut on the front side, then it will fall the other direction.
Yes, sir. That's depend on the. I'll explain that one also, sir.
Okay.
In later slide.
I get your point. Okay.
That's depend on the asymmetry of the bookshelf. And as I said earlier, this back books inside also became as a rigid one. So here also I compare the time history model with the analytical model for the compacted book inside, but I used reduced Hausner's coefficient. So this one is asymmetric bookshelf with loosened books inside. So we can see that some relative motion is there in books related to the bookshelf. So we just compare the compacted book inside and the loosened books inside. So overall, we can see the same results for the same applied ground motion. So we apply the same ground acceleration for the both different cases and we compare the results. So when we are applying that, when we are comparing the results, with compacted books inside have higher peak ground acceleration. As you can see, the experimental peak ground acceleration at overturning is with loosened books inside is higher. It's like the loosened books inside has a positive effect than the compacted book inside because of the energy dissipation. However, the difference is not that much, but still have some little bit positive effect when we are loosening the books inside. So this one, as sir asked me questions. So asymmetric bookshelf, this one, when we are putting the asymmetric bookshelf with the loosened books outside, nearly outside the boundary of the bookshelf, so this one become as a symmetrical specimen. So it is possible to overturn in this direction as well. So both sides are the same cylinderness are there. So that's what it's possible to overturn this direction as well, because this one became as a symmetrical specimen. So that's what is overturning is happening here. So we compare that one also. So this one is the comparison between our actual symmetrical blocks and the asymmetrical block with loosened books outside. Here the heights are different, but the critical angle ratios are same when we consider the asymmetric block with loosened books outside. So the experimental prediction also almost matching, even though heights are different. So we concluded that the critical angle ratios are more, is controlled much more than the height of the specimen. And this is our overall summary of our 64 cases. Here we choose Hausner's coefficient of restitution E1 and E2 because we don't know that each case, what are the coefficient of restitution, we don't know which one we need to use. So that's what, for the comparison purposes, we use only the Hausner's coefficient of restitutions. For symmetrical bookshelf, asymmetrical bookshelf, and other content inside also, still, when we are putting content inside the bookshelf also, it's pretty much better when we are comparing the analytical and the experimental. So now we'll move on to the fragility graph, because we, as I showed that, still we can predict the overturning using Hausner's coefficient of restitution. So we can go for the fragility analysis, the scope and limitations. So here, from the past studies, the sizing parameter limited from 0.5 to 2 meter. The sizing parameter is this one, R1. Then critical angle, the average critical angle is from 10 to 20. But in our case, we consider symmetrical specimen as also. So that's what the minimum angle should be 3 degree, and the critical angle ratio limited to 2.25. Okay, this one from the last year studies. In last year senior, he only considers three symmetrical specimen. He only consider 10 degree and 15 degree and 20 degree. But in our case, we consider this asymmetrical specimen also. Here, this is our this line shows the boundary of the asymmetrical blocks generally. So these are the points we choose, alpha 1 and alpha 2. Then each case, we consider sizing parameters 0.5, 1, and 1.5 and 2 meter. So totally, it will come like 48 cases. Comparing to the last year senior NEMA, he only considered 3 symmetrical specimen, but we consider a lot more than symmetrical and asymmetrical as well. So in our case, so as I said earlier, there are 48 different blocks we considered, and we choose 8 ground motions. Then we consider the ground acceleration, then flow acceleration for the 20th floor and 40th floor, and the 17th floor and 33th floor, and 11th and 23, and 6th and 12th. So totally, we have nearly 3,500 cases. So each case, we scale the peak ground acceleration or peak flow acceleration from 0 up to the overturning of each case. So we just increment like 0.001 g. So considering that we simulated like 500,000 simulations. So computational time, it took like continuous 20 days. So here I want to focus that I already explained that for the asymmetrical block, here we can see asymmetrical block, the alpha 2 is 4.5 and higher angle is 7.8. But when it's excited by the earthquake, this cylinder side exciting more. So it's controlled by the cylinder side. Even though it has the 7.8, but it's not rocking in this side, in this more cylinder side. It always rocking in this side. So, and we did the analytical results also. From these results, it shows that more than 98% probability it's overturning in these cylinder directions. So we concluded that this direction is the more vulnerable one. I explained that because when we are defining the capacity parameter theta or alpha, in asymmetrical case, there are 2 alphas are there. One is alpha 1, other one is alpha 2. So we don't know which one we had to use. So that's what, from these results, the minimum critical angle. So we choose the minimum critical angle for our fragility graph. So we consider like intensity, 6 different intensity measures. So Natapong choose the last year considering peak flow velocity. We choose the optimum 6 intensity different intensity measures from the past studies. Okay, now we'll go on the regression analysis. The regression analysis used to find the best fit graph, and we can find the best intensity measure to plot the fragility graph. So regression analysis, this is the capacity parameter theta over alpha 1. This is the minimum critical angle. So log of that, and this one is log of intensity measure 1. So here we can find that this is only for the ground excitation. Using 54,000 points, we got like R square value 0.42. For this one, for the ground acceleration, for the intensity measure 2, so nearly almost same. But when we consider the flow accelerations, it's like the amounts of data points are much higher, and the prediction of R squared also, IM1 have higher value than the IM2. So
wait a minute. Is it okay to look at this regression? I mean the line you came up with from the regression and this regression analysis. The R square value is very ugly. Should you maybe use something like just the boundary, or so like previous slides? I think maybe you don't need to get the line to represent the data point, but rather to get the line that represents the boundary of the of the data point, or so. I think that makes more sense than having like something like this, and then this line is representing my data points and R square is close to 0. and so it doesn't tell anything about the population to me.
So, Sivaram,
Yes, sir.
respond to this. You agree?
So I understand that, but still we can compare the results between IM1 and IM2. So I accept that the boundary line also we have to produce. That's true, but this is the best fit line, and this is the maximum R squared value. So there is no use of intensity measure 2. So here we can get like 0.225 because a lot of data points, and for the flow acceleration also. I still agree that IM intensity measure 1 is much better than the IM2 because this is what the maximum R squared value we got from IM2.
Well, this is not the way I look at your result. Actually, to answer Dr. Panche, this is not the equation he planned to propose. This is just intermediate step analysis to find
the best intensity.
Which intensity parameter will have a best correlation with the demand on this condition. So if we find that this is the best parameter, then we develop fragility function from that. So this is just intermediate analysis step to find the best intensity measure.
Yes.
This is not the target relationship to be produced.
Yes.
But then something at the intermediate is kind of a little questionable. So
exactly,
yeah, will you be happy to have like the final step information based on
final step look nice?
Okay, all right. Okay.
So as Professor told us, this is only for the finding the best intensity measure. So from this, we can easily ignore the intensity measure 2 because last year our senior chose this IM2 is the best measure. So this one for both ground and flow acceleration for IM1 and IM2. So IM2 is almost closely 0, so we can ignore the IM2. So, and this is the comparison between our last year senior. He has only the less amount of data, and I am not sure that he used only for the ground acceleration or flow acceleration. But here we consider both ground and flow acceleration, it's almost 0. So intensity measure 2 is not the best match for considering all type of blocks. So here I am regretting that the intensity measure 2 is not a suitable measure, which our senior chose as a best measure. Considering we consider the asymmetrical block also, and we consider a lot of flow accelerations, and sizing parameter less than 1.0 also not valid for the intensity measure 2. And this is the summary for all type of intensity measures. Sorry. So IM1, IM2, IM3, IM4, IM5, and IM6. IM4 and IM5 combination of IM1 and IM2. Here we can see almost IM1 and IM4 has somewhat similar R squared value. So here from this result, we can clearly choose that IM1 is our best intensity measure. Here for the IM2, when we consider the blocks with 0.5 meter, the R is the sizing parameter of the block, so it won't predict that much. So when we are using the intensity measure 2 means depending on peak flow velocity, we have to focus on sizing parameter greater than 1 meter. So finally, we choose the intensity measure intensity measure 1, peak flow acceleration is the best measure. So this is the derivation of the fragility graph. So we can assume that demand parameter and the intensity measure both can be random variable with log normal distributions. So finally, that's only depend on theta and beta. Theta is the median and the local standard deviation of the log normal distribution demand parameter. The demand parameter theta or alpha. So as I said earlier, we choose the best.
I think you have to speed up.
Yeah, because I have another one almost at 3 o'clock, so time is short.
Speed up.
Yes, sir.
Skip some slide if not important.
Okay, sir. This one for our fragility graph for the 40-story building. When we consider the limit state overturning, here the ground acceleration is shown here in the red line, and the flow acceleration is shown in blue and the yellow line. You can clearly see that the ground flow accelerations are more vulnerable than the ground excitation. For a particular intensity measure, so the flow acceleration has a higher probability of overturning. The same thing we got for the 33-story building. We can clearly see that the flow acceleration is more vulnerable for the blocks than the ground acceleration. This is for the 23-story building and 12-story building, and this is for the old type of buildings and the ground excitation. Still, the flow accelerations are more vulnerable than the ground excitations. So this is our conclusions. One of the main conclusions: the building components are more vulnerable to the flow acceleration in high-rise building rather than the ground accelerations. This one is past study. We compare our fragility graph with past studies developed by Daishano, and we compare our past studies ourselves with past studies by Petron as well. Petron
Sivaram, I think you can skip the details and go to the conclusion for this part. You have a good match or not good match?
So this is our final summary graph. So universal fragility graph for all type of block, including the sizing parameter varying from 0.5 to 2 meter. Here, this one is graphs for and significant rocking and minor rocking. So all the graphs are summarizing here. This is our conclusion. Our analytical model adapted from HouseNet can well predicted experimental results in both symmetrical and asymmetrical case. And we consider like 3,156 cases, as I told earlier. And we found that intensity measure 1 is the best measure for all type of blocks, and including asymmetrical blocks and flow acceleration as well. And our fragility graph for the ground motions are more comparable with the past studies. We compare the past studies results also. The content is like the block improve the stability of the blocks. It has positive effects. That's all.
The content inside the block, well, that is very it is subjected to some condition, I guess. Like if the content of the block locates like make the CG of the block shift up, then that is not improving the stability of the block. So it is like what uniform distribution of the content inside the block, probably. That is for your case.
Yes, sir. Yes,
if
sir.
you intentionally take off the bottommost 2 rows out and then keep the upper row. Okay, but anyway, it is just to make the wording a little bit.
Okay,
yeah.
Understand, Sivaram. I think the last conclusion need to be rewrite more carefully. Any more comments?
I do not have any more. I asked a lot on the way already.
Ajanavi, have anything?
No, I think it's very interesting. I mean, is it limited to certain types of shelves? Because what I see, the content matters a lot. What kind of content is that? And right now, it seems that the folders have a very certain type of properties which may affect. So is that reflected in the conclusion, or is just general content thing? Because I'm sure if it is food or sunglasses or some other things lying there, the response could be quite different.
Oh yes, sir. But for in our case, sir, even for the content inside the blocks, predict the our analytical model can predict the
No,
experiment.
my point is we are not considering the type of the content and its friction and other things and its own stability
Yes,
within the block, because we are assuming that they are very stable. But for example, if it's a glass or a wine thing, so it will topple by on its own axis maybe and fall down. So
Yes,
there are
sir.
many other things which we did not consider. I think the kind of folder that you have considered is a very stable content by itself.
Yes, sir.
It's very long and it's very solidly done. It has a high friction, so it's very stable content. So its response in this case will be quite different from any other type of content. So that's my concern,
Yes,
that
I
it
accept.
is not about the model is based on at least the verification is based on a certain type of content, and
Yes, sir.
that's something that you should mention clearly in your conclusions.
Yes, sir.
That's all. That's all. Otherwise, it's interesting, especially considering the recent earthquake in Japan and see all the videos of things falling out in a department store.
The recent one in Japan, in Chiba.
Yeah. The last couple of days, 2 days, 3 days ago.
Oh, I just saw the derail of the train.
Yeah, but there was a lot of videos posted on social media of the shelves in department stores and offices, things falling out, and none of them look like what we have seen here.
Oh, okay. Sivaram, I think you should go and collect that video. This day, I think a lot of interesting videos are taken.
Yes,
So
almost everything is recorded now. Nothing happens without being recorded. So anyway, I think it's an interesting thing, but I just feel that the content that we use inside will matter a lot in terms of how it interacts with the shelf.
Okay.
Thank you.
Thank you. I think Mostaba and Patipat, please leave.
Oh, yes.
Sivaram also.
Stop sharing the
Stop
screen
sharing.
and